Everybody, and welcome to the March edition of the Amateur Astronomers Association of Princeton. Most of you know me. I'm Rex Parker, the director of the organization, and we have a very interesting and enjoyable evening in store for you tonight. And so the way it's going to go, as is our wont, is I have a few announcements to go through and talk about some activities in the club. You can see some of them at the bottom. We'll save the hardcore discussions for after the presentation. We'll take an intermission, and then we'll come back after the intermission, and we'll have the Journal Club featuring John Church. I have another observer's challenge for you. You're going to like this one. We'll be talking about your plans, members' plans for the solar eclipse coming up, and we'll talk about things going on at the Club Observatory. So, getting into it now. We won't have a forum of that. Blocks it. Let me see if I can fix that. Well, we won't have a meeting here at Payton Hall next month for the obvious reason that it's the very day after the eclipse. And many of us, many of you, will be traveling for that event. Unfortunately, it's a fairly long distance to travel, so we're just not going to be able to put the logistics together for an event here at the next month's meeting. We put a very fine NASA eclipse link onto the club website. I'm sure you can find others on your own, but we think this is a particularly good one where the NASA people will be organized and showing the eclipse live from various locations. So check out that link on the AAAP site. We'll discuss other plans after the break. And is it going to let me move my slides? Well, I've had this problem before. This computer is not great at advancing slides in Zoom. I wanted to call out to your attention that Sidereal Times, our official newsletter of the AAAP, which is published online monthly, and a big shout out and thanks to Surabhi and her group, who are the editors and publishers of Sidereal Times, has a long tradition. And the new feature appearing in Sidereal Times, thanks to Mike DeMario, who's not here tonight, but Mike has championed setting up the astrophotography interest group. And it's been a very good thing. We've had a pretty nice involvement of a number of members. And so we're beginning a new feature in Sidereal Times. So check it out. Each month we'll have submissions of astrophotographs from members curated through Mike and the astrophotography subgroup, and make sure that they're well described, and they'll be in there on a monthly basis. In fact, this month,
hey Rex, we're getting a delay on the audio. We can't hear you.
Members published in Sidereal Times, and you can get that online. And just keep in mind, you can get back issues. They're all there on the right sidebar when you pull up the the WordPress document, the format that the newsletters in. You can get all the back issues. And I want to call to your attention our dearly departed member, John Miller. Many of us knew and were friends and learned throughout the years with John, one of our more active members for several decades, passed away sadly in November. And we talked about this. There's an article, sort of a tribute written up in the December Sidereal Times, if you didn't catch it. Anyway, we got we got an email from a family member, particularly through our member Vince DeRosso, is a good friend of John's, and there's going to be an event to remember John Miller at the Little Dinky Restaurant and Grill over here on University Place. Sadly, they picked a date, the Saturday before the eclipse, so that is what it is. But if you're not going away for the eclipse and you want to go check out other people who may be reminiscing about John, here's your chance. 12:30 to 2:30 on April 6th at Dinky Bar and Kitchen, I should say. And sadly, I won't be able to be there. Okay, let's get in a little bit of an astronomy mood now. Everybody knows that as March rolls around, it's galaxy season. Uncountable number of galaxies up there that are visible to us, even from central New Jersey through our telescopes or binoculars. This is a screenshot of the Sky 10 showing actually midnight right now, and as the weeks go on, this scene will become earlier and earlier each evening. That's the central meridian, it's purple there. And I'm showing you just the richness of galaxies. And I'm forgetting the setting of magnitude limit. I put this on probably 11, but it's uncountable even at that magnitude. And if you go to more faint magnitudes, it becomes, this whole screen becomes blue on the left side. So I really urge you to take advantage of this being the best time of the year. You've heard about Messier marathons. We're not going to do anything quite so bold, but we will be active out at the Club Observatory. So stay tuned to your email. Dave has already organized a couple of spontaneous night events where members are welcome to come out. As long as there's a key holder out there, a member can come. So take advantage of the opportunities. I've been able to grab a couple of nice images of some of the galaxies. This one I actually showed you last month. I like it so much I'm showing it again. But the Leo trio, if you will, the two Messiers, and never did figure out why NGC 3628, which is actually maybe the most impressive of these three, it's on the left, is not a Messier object. Like, how could Messier miss that one? But anyway, it's great because in less than 1 degree field of view, you get all three of these. So ride pieces or your wider field cameras can definitely capture these. All that spiral formation and star forming region. So I love this. I love this time of year, and it's just absolutely the best. But the observing challenge I want to bring to your attention. You, of course, are aware that we've had several observing challenges, all of which are open, by the way. Observing the South Pole region of the craters of the moon, where Newton crater, and if we ever got so fortunate, Shackleton crater, where the Artemis mission is aiming to land astronauts because there's evidence that there's ice in the deep shadowed craters. That observing challenge is still out there. I know some people are working on it. Tom has been working on it. I have been. Try to get an image when the moon is just in the right libration point in its monthly cycle where you can actually see the craters of the very southern tip. I talked to you last month about trying to image Jupiter and catch not a single but a double shadow transit of the moon's going across. That's out there waiting for someone. But the newest challenge, and maybe some of you saw this because the news media picked this up, this challenge is of different nature, and that is to observe and record the light curve of the impending recurring nova in the constellation Corona Borealis. We'll call TCRB for shorthand. T Corona Borealis. It's one of the most famous and the brightest of the novae that are recurring. There's not many of these. There are hundreds known in our galaxy, but only 5 apparently are known to recur, which means the cycle of their repeat is within the framework of modern astronomy when it has been reported by human astronomers. And the interesting thing about this is that, sorry, I don't know how else to do this. It's just playing havoc with me to advance the slides. I can come back now. Sorry, this is working. I can get it to work. Yeah. Okay. Is it working? We'll see. Here's a simulation of what this nova actually looks like, where it's a binary star system and the very large red giant is having its gases pulled off by this white dwarf you can barely see at the beginning, which reaches a point where the compression and the heat reaches a point in the white dwarf where it goes into a nuclear process and explosion. That's what we see as an outburst of light. And TCRB is thought to be on the verge of going to nova over the next 8 months. Now, how do we know this and what's the evidence for it? How difficult is it to see? We will talk about after the break, but where to find it. The observer's challenge is not only to see it, but to get its baseline before the outburst, which means since it can happen anytime over the next 9 months, you want to take advantage of right now where it's probably still is it could be happening tonight. But once it peaks, then you want to be able to capture images of it brightness, and it's only going to last a couple of days, and it's going to be decayed back on the baseline. So the idea is time domain astronomy. Here's a chance, a very rare chance, to actually image a new star that suddenly comes up to brightness, maybe magnitude 2, and then fades back down to magnitude 10, which is invisible even to most of our binoculars. So that's the challenge. You can talk about that after the break, as well as some of the other things I mentioned. I'm actually going to stop there, thankfully, and turn this over. And Victor, would you please come up and introduce our speaker for the evening? I'm going to hand the.
Okay, well, this evening's guest speaker is graduate researcher Erika Bernadette Hoffman. She'll discuss the physics of supermassive black holes at the centers of galaxies and the pivotal roles they play in the evolution of galaxies in which they reside. Ms. Hoffman will talk about how specifically high-energy disk winds launched from close to the black hole, detectable via their interactions with X-rays, have a strong potential to explain supermassive black hole galaxy relationships. She'll discuss new key insights into the underlying physics and overall impact of supermassive black hole winds and galaxies. Ms. Hoffman is a third-year astronomy PhD student at the University of Maryland, College Park, and a graduate researcher at NASA's Goddard Space Flight Center. She received a BS in astrophysics at the University of California, Los Angeles, and her MS in astronomy at the University of Maryland. While at UCLA, Erika did astronomical instrumentation research for the near-infrared spectrometer on the Hawaii Keck telescopes. In graduate school, she uses X-ray data to study supermassive black holes and their relationships with their host galaxies. She's also deeply involved in diversity, DEI, diversity, equity, and inclusion efforts, and she recently received an honorable mention at the AAAS meeting for her poster during the poster competition. So, thank you for coming. Thank you for Bill Thomas for suggesting that you come and visit us, and thank you. Here you go.
Thank you. Let's see if I can do that. Oh, perfect.
That's great.
Thank you. Thank you so much for the introduction. Also, if you can't hear me at any point, please just let me know. I hid all the controls, so I can't see Zoom right now. Yes, thank you guys so much for inviting me here. I am so excited to talk to you guys about some of my absolute favorite science, the physics of supermassive black holes. And as Victor already mentioned, I'm about halfway through my PhD program right now. And if you're not familiar with what that means, it essentially means right now I'm just working as a researcher under the direct supervision of my advisors, Dr. Anna Overzellick and Professor Christopher Reynolds, and they are experts in this field, slowly helping me become an expert in independent research as well. Okay, so to get into the fun stuff, what is a black hole? I'm sure you guys have all heard the word black hole before, but even me, someone who studies black holes, I still enjoy hearing how other people conceptualize black holes, because honestly, there's different ways to imagine them in general, and I like hearing about a little bit of all of them. So I personally conceptualize black holes as an object so dense that nothing, a physical process so strong, an object so dense that no physical process is strong enough to counteract gravity. And gravity is essentially controlling almost everything there is in what makes a black hole a black hole. They have two main parts when considering a classical black hole, one being the singularity, where all of the mass of the black hole is crushed into a singly dense, infinitely small point, but this point does have finite mass, which is important to remember because that means they do have finite gravity, not infinite. And it's that finite amount of mass that then defines where their event horizon is, which is often where we consider the edge of the black hole, because that is the distance from all of the mass from the singularity at which that gravity is so strong that nothing, not even light, is strong enough or fast enough to escape. And so because black holes are pretty much just mass and gravities then ends up being pretty much all you need to understand black holes in their most basic sense. So another funny way to conceptualize black holes is this funny phrase that a physicist describe black holes as, and it's that a black hole has no hair. And this might sound a little bit funny, but it's getting at this idea is that if you're trying to break down a black hole into what few things you can describe it as, you can describe it almost entirely by its mass. So as an external observer, like me and all of us, we're not inside a black hole as far as we know. And that means if you're trying to think about it, compared to other objects in the universe, black holes are somewhat strangely actually quite simple. I'm not trying to say that to sound cool, just that because they don't have to balance any forces like most other things in the universe, like where I'm standing right now. Gravity's pulling me down, but the Earth is pushing back up. Black holes don't have to worry about any of that. They don't have to balance anything because everything is just crushed into the center. And just to think about what makes a black hole unique, and it's what is going to get at why they're unique and important to study for me, is that their gravity close to them is very, very strong, because gravity just depends on distance and mass. And so that means to feel the strong gravity, you actually have to be very, very close to them. And so this is just some quick diagrams of what depict potential wells, which are kind of like trying to express gravity in 2 dimensions. And since I'm an observer, we can just forget about everything past the event horizon. We don't care about that. I mean, sorry, it'd be interesting, but sort of irrelevant for me right now. And you can just think about where black holes are most unique is if you're really, really close to them, like you're in a really, really near orbit, or even if you can still be in stable orbit, but really close to them. It can be somewhat similar, essentially the same to when you're orbiting other objects. And then if you're really, really far away from a black hole, they're not really special anymore because gravity's just gravity. Okay. So of course, this talk isn't just about any black holes. We're talking about supermassive ones, and pretty much all we mean by that is if you were looking at black holes across different masses, we have on one end, we have what we call stellar mass black holes, which just means that they're on the order of the mass of a star, like our sun, like maybe 1 solar mass or 10 or 100 solar masses. And astronomers, we're very self-centered. We compare everything to our sun here in the solar system. So that's why everything on this scale is relative to our sun. And so 1 to 10 to 100 times the mass of our sun, that's a stellar mass black hole. But I'm in particular talking about way on the other far end, something that is at least 1 million times the mass of our sun. So we're talking way, way, way bigger. And these can be pretty often even 1 billion times the mass of our sun. So when I say supermassive, I'm just meaning this particular mass range of 1 million to 1 billion times as massive as our friendly star. Okay, so where are we finding supermassive black holes in the universe? And that is at the centers of large galaxies. That is the only place we've ever found supermassive black holes. And at the center of every large galaxy, we are pretty sure there probably is a supermassive black hole at the center of every single one. And when I say large galaxy, I mean something essentially as big as our own, like the Milky Way. And these are often most commonly spiral galaxies. And this right off the bat is really suspicious. Like, why do we always see supermassive black holes at the center of galaxies, and why is it so common for large galaxies to have these supermassive black holes? Why are they important to each other? What is the relationship between them is the question we get just from knowing these simple facts. And one interesting thing that the relationship between them definitely is actually, like I was mentioning before, is actually not a gravitational relationship. Galaxies are by no means scaled up solar systems. Just to give you an example, our solar system, most solar systems like ours, are in fact dominated by the mass at the center. Our sun makes up 99.8% of the entire solar system's mass, and we're all in scale of the universe relatively close to the sun, and that is what is dominating all of our orbits. But if you take some average large-sized galaxy like Andromeda, which also has a pretty averagely sized supermassive black hole, even that supermassive black hole is less than 1% of the entire galaxy's mass. And the galaxy is so big that the supermassive black hole is kind of gravitationally irrelevant to most of the galaxy, if not all of it. So definitely do not think of galaxies as scaled up solar systems. Their galaxies are much weirder, their dynamics are much stranger. So then, if not gravity, if you look deeper into what's going on between supermassive black holes and galaxies, it gets even weirder, because if you look at something, for example, this first figure on your
Left.
yeah, the one with the galaxy picture on it. The x-axis is stellar velocity dispersion, and the bulge of a galaxy is, if you look at the classic picture of a spiral, it's the bright part about the center quarter of the image. We just call that the galactic bulge. And so strangely, the average velocity of stars in that bulge seem to correlate with the mass of the supermassive black hole. So if you look at a range of different galaxies, the larger the supermassive black hole, on average, the faster the velocity of stars will be there, which is really weird if they can't possibly reach these stars gravitationally. And then also, if you were, in regards to the other figure, if you were trying to simulate galaxies in the universe, you're trying to go from an earlier galaxy to a later one and see if you could recreate the amount of small and large galaxies in the universe. This would be something people often try to simulate, and you can't correctly predict the amount of small and large galaxies if you don't take into account the effects of what's going on at their various centers. And so this is just a broad relationship. The bottom is galaxy luminosity, x-axis, which just generally correlates to galaxy mass, and the y-axis is the abundance of how many of those galaxies do you see. And you can see the red line and the blue line don't line up at this lower end if you don't account for the centers of galaxies. So they definitely have a lot of interesting relationships. So what we have to do is try to understand how. So the first piece of understanding how galaxies and supermassive black holes are related is understanding what is an active galactic nuclei. They are essentially just the region directly around the supermassive black hole. So we're talking outside the event horizon, so that's why we can see it, but still really, really close to it. And in this very small region at the very, very center of galaxies, you actually get extremely high luminosities. And when I say really, really high luminosities, I mean this small region around a supermassive black hole can outshine the entire galaxy that it resides in sometimes. So we're talking this small region can outshine over a billion, hundreds of billions of stars. And so when astronomers first discovered the centers of galaxies, these active galactic nuclei, it was really confusing because stars were some of the most powerful things we knew and some of the longest lasting things we knew. And now all of a sudden we're seeing something billions of times brighter than that in a much, much smaller space. So this really puzzled astronomers for a while. But don't worry, we have a lot of the big ideas figured out now, and they're actually really, really important to explaining these galaxies' relationships, and that's because these active galactic nuclei have what we call feedback. And when I say AGN or active galactic nuclei feedback, I mean not only outflowing radiation, which is their bright luminosities, but it could also literally be matter outflowing from these small regions. And it could be in the forms of jets or winds. And when I say jets and winds, I do mean probably whatever you're imagining as a jet or wind right now physically. A jet would be something that's super collimated and focused and really powerful in one direction, but a wind might be over maybe a larger area, a little bit more turbulent, and just a little bit less organized, but maybe still powerful overall. So to understand active galactic nuclei, we really need to get into what an accretion disk is. And accretion, if you're not familiar, essentially just means how you collect matter in some way or another. And an accretion disk is a disk of densely packed orbiting particles that are able to slowly get closer to the central object by shedding energy via friction. And it's really important to think about how are particles able to shed energy, because in any normal orbit, if your orbit is going to decay in any way, there has to be a reason. So it's really important to think about this shedding energy because that is what makes disks bright, because that is what gives them heat. And then this is also what leads them to actually ejecting matter. And this is just a little diagram showing you different angles of what an accretion disk might look like and how things are orbiting faster in the center. And don't worry about the weird angles of it, those are just from general relativity. And so when you're trying to think about the details of what is going on in an accretion disk, that actually has this really interesting consequence that might go against how the media might make us think of black holes, and it's actually way harder for a black hole to gain mass. We always think of black holes as attracting everything towards them, but really it's way more complicated than that. So we really have to think about that, and it becomes, again, really important for active galactic nuclei. So just a quick little brain teaser to get you to think about why do particles in the accretion disk, why do they need to shed energy to lose their orbit? And so I'll start out with this question. If the sun was replaced by a black hole of the same mass and put in the exact same place where the sun is right now, would Earth's orbit change? Sadly, this isn't like Astronomy 101, so we can't have like a cute little discussion. But you can think about that for a second, and I'll tell you the answer, and that is no. If the Earth's orbit were to change in any way, there would have to be some reason for why it changed. This goes back to the core principles of gravity, is that gravity depends on mass and distance. And in this question, I'm not changing the mass of the central object or our distance from it. And something has to cause you to spiral. Although the scales for this situation are different than accretion disk, we're a little bit farther away from the central object, but it is important because it's getting at that you really need to end up shedding some kind of heat and light and injection of matter to actually so-called accrete matter. Okay, so why does thinking about an accretion disk and all this matter outflowing help us? It's because black hole accretion is actually the most efficient, sustained process at converting matter into energy in our universe. There's nothing that even comes close to lasting as long and having the same efficiency, this high of efficiency at the same time. So we're talking about a 40% conversion of turning matter into pure energy. And this is the E equals mc squared equation that Einstein is pretty famous for. And if you're not familiar with the E equals mc squared, it's getting at this idea that all matter has some sort of intrinsic energy equivalent to it. So you can think of matter even doing nothing, or what physicists call rest mass energy. Even matter doing nothing has some sort of energy equivalent to it. And the challenging part is tapping into that energy in any way. So for example, this 40% mass energy equivalence might not sound that impressive, so I'll give you some things to compare it to. The efficiency that the nuclear fusion in stars converting matter into energy, the things that holds them up for millions or billions of years, that efficiency is less than 1% at best. So black hole accretion really knocks them out of the park. But to give you a more sort of daily life example, I can't really, because you would never measure daily life energies in this way. But if you took something like gasoline engine efficiency, you're getting, barely measurable, less than 2 parts per million of the possible amount of energy you could be getting out of matter. And so this is really important because this means that now we're talking about supermassive black holes. Their accretion process is the most powerful, persistent process in the universe. And this really explains, finally, why our AGN is so bright. So it really helps us figure out this big question. And this sort of gets to sort of a general big thesis idea, or thesis something, I might be doing sometime soon. And it's this whole sentence we've been working on, which is supermassive black holes co-evolve with galaxies via accretion-powered active galactic nuclei feedback, and this feedback is in the form of radiation, jets, and winds. And this is just a diagram showing you the relative orientation we think that jets and winds probably are in regards to their black hole and the accretion disk. And it might sound like, maybe we have this all figured out, maybe I laid it all out for you, maybe you understand, maybe you don't. But maybe we have it all figured out. Well, don't worry, we do not, because that would mean I'd be out of a job. There's still plenty of questions we have left to figure out. And just to give you an example of some of the ones that I'm trying to help figure out, it's, for example, which of these processes is most important? I've listed things like radiation, jets, and winds, but among even those three things, is one of them more powerful than the other? Is one of them stronger or more important in creating these relationships with galaxies? And even if we are to pick one of these processes, I'm a physicist by training. What is the physics actually going on with these processes? And what I'm going to be arguing the rest of this talk and probably the rest of my PhD thesis is that it's highly probable that highly energetic winds have the strongest potential to explain this AGN feedback that I'm talking about. And then what you want to figure out after that is, if we think AGN winds are the strongest potential to explain feedback, where exactly are they launched? How are they launched from the accretion disk? Like, what are the actual details of what's going on? And then, of course, are they actually powerful enough to explain these massive galaxy-wide relationships? Okay, so what do we know so far about AGN winds? Well, they are on a range of scales throughout the galaxy. This figure is a logarithmic scale. I apologize if that's confusing. Essentially means exponential. You're going down from very, very small regions to very, very large regions really, really fast. But this diagram is just meant to show that there's a lot of different kinds of winds at different scales. And they're generally all very, very hot, moving very, very fast, anywhere from a couple 100 kilometers per second to somewhere close to the speed of light. But I, in particular, study the winds that are the closest to the black hole, the closest innermost parts of the accretion disk, and these are also the hottest and the fastest of the different kinds of winds you see in AGN. If you were to go out and observe an AGN, you would probably see winds of some kind at some scale, and these particular winds that I study are definitely in about more than half of the AGN that we see, so they are fairly common. So again, thinking like an astronomer, if you want to find out more about these AGN winds like me, how do you want to go out and observe them? So active galactic nuclei, like I said, are very, very bright. But not only are they very, very bright, they're bright in almost every single wavelength of the electromagnetic spectrum. They're bright in both infrared, visible, ultraviolet, X-ray, and even gamma ray. And although radio is not on this graph, they can also sometimes be very, very bright in radio waves as well. So if you're trying to study the closest winds to the black hole, which wavelength might you want to study them with? So UV or ultraviolet light would be honestly a really cool way to study winds. I, in some ways, wish that I could, but sadly, you run into the problem that our own galaxy actually gets in our way. If you're trying to do extragalactic astronomy in the ultraviolet, our own galaxy will absorb most of the UV photons that you would want to be studying. So that whole range is kind of not possible for this line of research. And then another really good range that I have a lot of coworkers and peers that do study AGN in the infrared and visible light, for example, with James Webb Space Telescope. It's a really cool way to study AGN, and they can study winds at different scales, but because infrared light and optical light has just so much going on, as you can see in this graph, you're also getting light from the galaxy in optical because, remember, stars are really bright in optical. And then things can also get in the way a lot more easily with infrared and optical light. And so if you're trying to look at the absolute smallest regions at the center of another galaxy, it probably isn't ever going to be super great to look at them in optical and infrared. So then what part of the electromagnetic spectrum is left? Well, X-rays are the best rays, or at least as I like to call them. And because X-rays can both penetrate dense regions from from the galaxy it originates from and our own. They can pass through a lot more matter more easily. And because X-rays are emitted in particular from very, very close to the black hole, the innermost parts of the accretion disk, if you really want to study these innermost regions, X-rays are by far the best way to look at AGN. And also due to other physics reasons, if you're trying to study these extra hot winds like I am, they're actually invisible in most other wavelengths of light. So there's a lot of reasons why I would try to get you guys on board with me that X-rays are the best rays. And this is also just a diagram showing that there's just a lot going on in infrared invisible light. So that's why it'd be really interesting to study, but hard if you're trying to focus on the innermost regions inside that donut part. Very, very center is where the black hole and the accretion disk actually are. Okay, more trying to convince you why X-rays are so great. So active galactic nuclei are actually the strongest sources of X-rays in the universe. Really nothing else compares to how many X-rays they put out in the universe. They even got, it's very, very different than the cosmic wave background, but they even have their own word of the X-ray background comes from other AGN distant in the universe. And pretty much the point of me saying that is that means that X-rays are actually also the main identifier of an active galactic nuclei. If you're looking at the center of a galaxy in another wavelength, like visible or infrared, and you're seeing a lot of things that make you think, oh, this might be an AGN, but you're not sure, all you do is get an X-ray observation. And if you, for example, in this little Chandra X-ray square, if you go take an image of it and you see something like in this image, a really, really bright white dot at the very, very center, you go, oh, yep, that's an AGN, I was right. And just to admit, there are X-rays, other things in the universe do emit X-rays, but nothing is quite as strong as AGN. And this is just another example in the optical, the next panel over. Is very, very bright, but you're almost washed out by all the other things that are also happening in galaxies in optical wavelengths. Okay, so now we're going to get to essentially the cons of studying things in the X-rays, and that is sadly that X-ray astronomy is not your backyard astronomy. That is for some very good reasons, but that essentially means that the atmosphere of Earth will completely absorb X-rays so that almost essentially zero ever get to the surface. So you can't do any kind of astrophysical X-ray observations from the ground. So that means if I'm going to observe anything astrophysical in the X-ray, I have to be using a space telescope. There's no other options for an astronomer like me. But I have this funny list. No, I don't know why anyone would make this list. I don't know why I did, but if someone were to make a list of the pros and cons of Earth's atmospheric shield blocking us from seeing X-rays, we would say, as an X-ray astronomer, I would say the cons are that you can't do X-ray astronomy from the ground, and the pros are life as we know it is able to exist. You know, who would make this list? Who would make this list? But yeah, a couple of medical X-rays in your life is not going to hurt you, but if we were bombarded by X-rays all day, every day, that would be bad. Okay, so more things that make it difficult to study active galactic nuclei or their accretion disks in particular, and that is that they are generally too small and distant to actually spatially resolve or angularly resolve. In other words, this means we actually can't image supermassive black hole accretion disks or really any black hole accretion disk because they are just too small on the plane of the sky. And so we have this great image, this Hubble Space Telescope image of a spiral galaxy that has a known AGN, but what is going on in the very, very center? Big question marks. Obviously we have ideas that I'm telling you all that we know about AGN, but generally when it comes to like the geometry or the spatial way things are laid out, there's still a lot of open questions. I had to restrain my musical theater kid self to not call this slide lies, because they're not lies, they are scientifically motivated artist impressions. So essentially every black hole accretion disk diagram I've shown you so far. They are scientifically motivated. We know that there's a black hole there, we know that there's a disk there, and we know that it's bright. But details other than that, like how exactly would it look, there's still a lot we don't know, because galaxies are way, way easier to image just because they're way, way bigger. And I know you guys had a really, really cool talk not too long ago about the Event Horizon Telescope. So I did want to quickly address the differences, and that is the Event Horizon Telescope was able to resolve the absolute closest two supermassive black holes to us. So that's our own galaxy and the next closest galaxy, M87. And they did resolve those, and they are supermassive black holes, and they are galactic nuclei, but they generally aren't considered active, or at least I would not consider them active. Sometimes when I talk to other astrophysicists, they say, no, they're just low luminosity AGN. But as I can explain in this slide, low luminosity AGN, I feel like kind of defeats the definition of an AGN if we're talking about something that's supposed to be extremely luminous. And just so it doesn't sound like I'm just being picky, I'll quickly explain kind of the regime that active galactic nuclei generally are. If you are curious about the jargon, this is sometimes called like the Eddington regime, and that essentially means if you have something super, super bright and you ask the question, how bright can it get before it blows itself apart from radiation pressure? Where at what point does this object get so bright that its own radiation pressure blows itself apart? And active galactic nuclei, generally on this graph, which are plotted, love to dance really, really close to the maximum possible brightness they can be before they blow themselves apart. And then if, so it's the y-axis is AGN luminosity and the x-axis is their mass, because this relationship generally changes with how massive they are. But if we were to try to plot M87 and Sagittarius A on this same plot where we have these super, super bright AGN, the dots don't even make it on the slide. They're more like halfway down this wall. So that's why I wouldn't generally consider them active. But that's not to say I wouldn't still absolutely love more images from them. I'm not saying that. I would love an image of any accretion disk of any kind. My only point is that what's going on with them is generally very, very different because they're just doing very different things. But then if that was too much of a downer for you, I do have some more pros for this, and that it is probably good that Sagittarius A, our supermassive black hole, isn't particularly active, because that would also mean a ton of extra radiation in our galaxy. That would probably also make it difficult for life on Earth as we know it to exist. So that's just a pro to cheer you up for a second. But if you're curious why our galaxy and M87 and the nearest galaxies, supermassive black holes aren't active, it's not just by chance, not just bad luck. It's also related to the fact that we think that active galactic nuclei are generally more active a little bit earlier in the age of the universe. And they probably peaked around a redshift of 2, which is, you're not redshift are weird, but that's about 3 million years since the Big Bang, and right now we're about 14 billion years after the Big Bang. But to study them, you don't need to look back quite that far. You don't need to go super deep into redshift. But you do want to look at least a little bit farther away to try to get them at least in a slightly more active time in their life. And this graph is just showing that generally, as you go farther earlier into the age of the universe, how AGN generally are more abundant or brighter earlier in the universe. Okay, so it might sound like if we can't image the thing I'm studying, how do we know anything about it? But don't panic, imaging, as a lot of you probably know, imaging is not the only way you can do astronomy. Imaging is probably just the most accessible way to talk about astronomy because we're all pretty familiar with a camera. It's pretty similar to how our eyes work, but spectroscopy is a little bit different. Instead of thinking about spatial position versus brightness, instead you're thinking about looking in a single direction and saying, what wavelengths of light in that single direction am I getting? So if you're thinking in terms of if light in terms of particles, you would be looking in one direction and saying, counting, and being like, how many blue photons am I getting versus how many red photons am I getting? yellow photons. And you need more than just a camera to do that. You need an additional tool, something like a prism or water in the sky after a rain, turning generally white light into a rainbow of light, or as scientists use things like diffraction gratings. And it's because our eyes can't naturally organize light into its different energy wavelengths. You need another tool to do it. It's just a little bit harder to explain to people, but things like the James Webb Space Telescope tried to also do press releases with spectroscopy too. This is just one of their press releases, because arguably you can actually learn more, if the same amount, if not more, from what you're studying with spectroscopy. For anyone who might not be familiar with how astrophysicists use spectroscopy, we can do it to determine composition, what elements are we looking at. We can also use it to determine what something's velocity is coming directly towards or away from us. And also generally, physicists would get mad at me for equating temperature and ionization, because they're not exactly the same thing, but they're getting at this idea that with spectroscopy, we can generally figure out what is the energy in an atom or in its electrons when we use spectroscopy. And then also you can figure out density, because depending on how many atoms are in your way or emitting the light, you will get different spectroscopic results. And these are all great things when you're trying to learn more about active galactic nuclei winds, because we can find out what winds are made of, how much energy do these winds have, how fast are they coming towards us, and how dense are these winds. And just because I'm trying to do a little bit of both lower level and high level stuff for anyone in the room that isn't familiar with spectroscopy or how we use it in astrophysics, I'll quickly do a super fast crash course in this. If you already know what this is, I apologize. But for those of you who don't, also if it's your first time hearing about it, know that even in my undergraduate career, I don't think I was super comfortable with spectroscopy till towards the end of it. So just know that, take whatever time you need to try to figure this stuff out. But the quick crash course in spectroscopy is the main idea is that electrons in atoms are picky eaters. They only want to interact with very, very specific wavelengths of light. So that means electrons and atoms will only absorb or emit very specific wavelengths. And based on which one of these wavelengths they emit or absorb, we can determine not only the element, but this is the specific orbit level in which it's changing. And then another interesting thing, which people are often less familiar with, is we can actually determine the specific ion of that element, which is really important for me because I'm trying to study winds and their energies and their temperatures, and I want to know how many electrons are actually left in that atom, because that will generally tell me like what state of matter it's in, and also how hot it is in that state of matter. And this is just a diagram showing, again, if you weren't familiar with spectroscopy, how you can use each element's particular interaction with light, what light they want to emit or absorb, and you can use them all as fingerprints, because laboratory physicists will do really important work where they will figure out all these specific wavelengths in which light will, in which atoms will emit and absorb light, and then they put them all on these massive databases, and then those get put into the models that people like me use when I'm trying to look out in the universe and figure out what exactly am I looking at. We can use these fingerprints to decode them. And then I'm also looking at using spectroscopy in a very specific way. So the examples I've shown so far are sort of like emission line spectrum, where if you take a hot gas of a single element, so you put like hydrogen in a tube and you heat it up, all the electrons will go to higher orbitals, and then when they drop down, they will emit only the specific wavelengths of light. But I'm instead looking at a combination of two things. Different physical processes in the universe can create a continuous spectrum or a rainbow, something like that we're familiar with. And if you take a continuous spectrum and then put something colder to it, just relatively colder, it doesn't have to be literally cold like we're familiar with, just something colder than the original source in front of it, then those colder elements will, atoms will steal only very, very specific wavelengths from that. And so this last part on the figure here, where we can take whatever continuous spectrum and then what is missing from that spectrum to learn about these sources, or what is going on with the winds. And so if you're thinking about the context of active galactic nuclei again, now we're thinking about how there is an X-ray source due to super hot and high energy physics happening really close to the black hole, but then on their way as they're traveling towards us, they pass through these winds that are colder relative to the original X-ray source, and therefore some of the X-rays end up being missing from our spectrum. And based on what what wavelength those electrons steal, we can figure out what is going on with them. So this is just an example of the Chandra X-ray Observatory, like I have been using data from. So the particular smudge I am studying right now is AGN SQ63015, barcode of a name, and the winds in particular are all in a state of matter known as plasma. If you're not familiar, it's atoms or gaseous atoms which are so energetic that some of them have lost control of their electrons. And when I'm studying them, I use astrophysical plasma simulations to model the spectra that I'm seeing. If you want a little sample of the kind of data that I'm looking at, this is wavelength on the x-axis and flux, which is essentially similar to brightness on the y-axis. And depending on what kind of spectra I get, I can use the plasma simulations to actually model the velocity and density. And like I said, we're something similar to temperature when studying these winds. And you can see, like right here in this example, where this spot where the X-ray got stuck would correspond to where I'm missing some of the X-rays in my spectrum. And to think about spectroscopy in the context of astrophysics, like I already mentioned, you can use the position or the energy of the line to determine the element, the ion, and the energy. And then if there's any kind of shift in the line from where we expected that wavelength to be, then you can use the Doppler shift to determine how fast these winds are flowing towards us away from the accretion disk. And then also you can determine not technically 3D density, but at least a two-dimensional version of density, because that just corresponds to how deep your lines are, or how many atoms were in your way and able to steal some of your X-ray photons. If anyone has questions about the Doppler shift, you guys can ask me later, but I know there's a range of knowledge here, so I can keep going for now. Okay, so I'm not a big fan of equations, especially when trying to do public talks, so I'll instead give you intuition for how are we using these measured properties to better understand what is going on with these winds. So generally, when we take something like what particular ions of these elements is in our spectra, we can use that, which is generally a somewhat similar concept to temperature, and we can actually use that to figure out an approximate distance of where are these winds relative to the source they were emitted from. And so a similar intuition concept you can think of this is if you told me how hot your campfire was and how hot you were, I could then extrapolate the distance you were from your campfire. And so that's kind of a similar concept of how we can determine with large error bars where these winds are. And generally we can also figure out how powerful they are by getting as good a constraints on density of these winds as we can, because you can use density to then determine how much mass is in these winds coming off of accretion disks, and then like the velocity, we can also measure them. We can use that to generally estimate their wind power. And just a quick example of intuition of how mass and velocity help us estimate wind power. You can think of how a fast-moving truck filled with a lot of stuff in it will have more power than a slow-moving truck with nothing in it. So those are just quick appeals to your intuition, because So what am I doing in particular? So currently I'm actually reanalyzing X-ray data from over 20 years ago, which might seem a little bit strange off the bat, but if you think about how much technology changes all the time, how much physics gets improved all the time from this new technology we have, there's actually a lot of stuff we can still learn even from this old, really good data, honestly, from over 20 years ago. And some of the new things we have that I can now analyze these spectra with is that we actually have improved plasma models. Like I said, when we're trying to even just determine what are the exact line positions of all these different energies, laboratory physics and simulations, those are constantly getting better. The databases are being improved. And then also when we're trying to model these regions very, very close to the black hole, sometimes we have to take into account general relativity, if you're familiar, which is just really weird effects from extremely strong gravity. And so models like those have also been getting better in recent years. And then since this isn't a statistics lecture, I won't go into statistics at all right now, but also generally, there's a lot of really new interesting methods into statistics of if you're trying to compare, different physically motivated models, for example, with these regions where we can't resolve them. So there's a lot of open questions of like, how are things arranged? What might actually be explaining some of the spectra that we're seeing? We can use statistics to mathematically motivate which of these models actually truly best represent the data that we have right now. And then also this last 20 bullet point that I call new computing power. I was showing this kind of phrasing to my computer science friend one time, and they were like, supercomputers aren't really that new, right? And I was like, well, to astronomers, they're kind of new, relative to, astronomy is one of the oldest sciences in the world, so relative to that, supercomputers are still kind of new. And so, especially in my particular niche field of AGN winds, using supercomputers to actually compute these models really, really carefully and model spectra that I'm looking at. And then also this last bullet point of I'm actually able to determine new constraints on the three-dimensional version of density, which is actually more important than just 2D density, if we use supercomputers to more carefully calculate some of these plasma models. And so that is some really cool stuff that I hope to contribute to the field in the near future. And also, like I mentioned to some of you already, in September, there was actually a completely new X-ray telescope launched. It is the X-ray Imaging and Spectroscopy Mission, also known as PRISM, and it was launched by the Japanese Space Agency in partnership with NASA. And it's actually going to study X-rays in a completely new way with a totally different type of spectroscopy. And it's going to generally just have really, really good resolution, so we can actually get more details out of the spectroscopy that we'll be doing. And yeah, I have the summary of all my slides on here, but I know I said a lot of things, so we can also get into whatever your guys' particular questions are. Thank you. Yes.
Do you need new data sources from, say, the Japanese or Chandra to complete your research? Do you need new data sources?
So, in particular, I could actually.
Could you repeat that question?
Oh yeah. So the question was, do I need new telescopes to complete my research?
New data.
Yeah. So actually, right now, because I am applying so many new methods, there's actually a lot I could learn just from archival data. I'm actually studying completely publicly available archival data right now, which is kind of funny. But there is a lot of work I could do with that. So although new data is totally great because that means we can get a new look at it and then also a new time on it. So it's like if we want to study AGN variability over years, a new observation would be really useful. But especially for some of my grants when the telescope hadn't launched yet, I definitely phrased it as I don't need it, but I would still like it, yeah. Yes.
What is the actual resolution capability of the X-ray telescope set, like the new one you talked about in existing ones?
So since I'm more on the spectroscopy side, I don't know off the top of my head what the imaging capabilities are, because they still won't be useful to me. So I could look that up later if you're curious. But yeah, I don't know off the top of my head. Yes.
Why in specific do you believe that the winds are the strongest source of the AGN luminosity?
Oh yeah, that's a good question. I definitely should have touched on that more. So because they're emitted from so close to the black hole, And there's some of the hottest and fastest winds that we see. It's actually a strong possibility that they're a catalyst for the winds we see at larger scales. So I mean, we haven't confirmed things like this for sure yet. There's definitely a popular idea that these winds really, really close to the accretion disk are then what start these winds at other scales and things like that. And also, since they're the hottest and the fastest, they might generally just be able to have the most power at pushing other gas and heating up the rest of the galaxy. Yes.
Yeah, how large does a galaxy have to be in order to get a supermassive black hole at its center? I mean, they come in many different sizes.
Yeah, yeah.
What's like the minimum?
Yeah, minimum, I'm not totally sure. I definitely know things like irregular galaxies and dwarf galaxies. Those, can be hit or miss on whether you see like a black hole at their center. But in terms of definitely spiral galaxies, you'll almost always see a supermassive black hole. But if we're thinking about galaxy morphologies, we're getting a little bit outside my wheelhouse.
You need a certain large mass in order to get this happening. For
Yeah.
example, look at the Magellanic Clouds. I guess they don't have any supermassive black holes in them, do they? They're
Yeah, as
small.
far as I know, those are pretty small
Yeah.
galaxies.
So there must be like a minimum size before you can get this happening.
Yeah, I mean, that is also touching at the idea of the dynamics of do they grow together, there's some questions we don't have answered yet of those galaxies, like I mentioned, like dwarf and irregular, where we might not observe a supermassive black hole. Maybe there is, something like an intermediate mass black hole that we just can't observe for whatever reason, because maybe it's not active enough or not interacting with enough. So it's we can say that we can't observe things in those smaller galaxies, but we can't say for sure that it's not there, because there's a lot of questions we don't know yet. Yeah, it might be there,
but probably not in the Magellanic. So.
Yeah, I'm not as familiar with the Magellanic Clouds, but I'm pretty sure those are kind of small.
They're pretty small. They're like satellites around them.
Yeah, we definitely want something really big, like the Milky Way.
Hi, Professor Hoffman. If you can hear me.
When you say the winds, what is this? The matter whirling around the accretion disk?
Yeah.
In the accretion disk, or is it stuff being blown in a different direction?
Yeah. So I mean, again, since we can't image them, I can't really tell you their geometry for certainty. But generally, the disk is, that is something, even though we're fairly certain about. There is some dense disk that we can't see through. So the winds then have to be something on top of them so that we can see them on our line of sight. And then again, generally, since we can't image them, we know that they're in the way, and I can guess their geometry. But I don't know how we would pin that down any more, if that makes sense. But you could definitely look at, although I don't have any cool videos, people who simulate disks with fluid dynamics, they can somewhat easily actually create winds of some kind that come off at, I think usually less than a 45-degree angle from the disk. But simulations, can't include everything. So it's can sometimes be hard to be sure what you want to take from those simulations. Yeah.
Well, when you say winds, it sort of conjures up an image of a moving gas.
Yes.
Of various temperatures, volumes, directions. But where do the X-rays come?
Yes, so that's something I totally jumped over in this talk. But the X-rays generally come from this funny thing we call a coronae, which is similar to the word we use to describe how hot things get around the sun. But the coronae, this relates to a little deeper physics on the shape of the continuous spectrum, and the shape of the continuous spectrum of the X-ray source gives us an idea of what is actually emitting those X-rays. And because it's this specific characteristic cutoff power law shape that actually gets at them being highly super duper fast on what we call relativistic electrons, that are actually taking photons that originally come from the disk, because the disk is, like I said, really hot and emitting light, but those in particular peak in the ultraviolet. And so that it's then, we think, disk photons go into this coronae wherever it may be, because again, geometry is totally unknown, somewhere close. That's why I said somewhere in this image, somewhere close to the black hole. And so the disk photons go up and then they go into this hot coronae where the electrons are moving so fast, they actually give the photons energy and bump them up into higher energies of X-rays. And that is the main X-ray source that we see.
Okay, and how are they detected? I mean, you have pictures of a prism there, which is sort of the business end of the spectroscope. What does an X-ray spectroscope look like? How does it detect and separate the wavelengths in X-ray?
Yeah, so that's a good question. And actually, it depends on the telescope. For example, the one I'm picking here, the Chandra X-ray telescope, the one that I use, that is the diffraction dispersion grading. High energy transmission spectrum. Sorry, it's a transmission grading. So that means it's something that separates the wavelengths, but lets the wavelengths pass through them, and then it goes. I apologize, I'm not an instrumentation person, but that means that the photons go through the transmission grading and then get separated. But then, for example, the CRISM telescope is a completely new kind. It's not grading, it's not even dispersing any light. It's actually a new type of spectroscopy called a microcalorimeter, which is a fancy word for meaning that it's like a really, 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 really good like thermometer. So they cool it down like as cold as they can get it. And then as X-ray photons come in and hit the detector, they're actually detecting the change in temperature that X-ray photons make. And so that's actually a really cool, new, interesting way that they're doing things. Yeah.
It's interesting. Is that like the, what do you call it? Edison, Thomas Edison invented a gizmo like that. A really sensitive thermometer to try to observe the eclipse. He wanted to, I think, try to see what the temperature of the corona was.
Yeah, because our sun does definitely emit some X-rays. So yeah, I'm not familiar with that, but you might.
Wow, it's pretty cool.
Yeah. So it was actually the first, fun fact, the first X-ray detectors were pretty similar to Geiger counters because this is this ionizing radiation. And so I mean, we've come a long ways from Geiger counters because those don't tell you as much information, but yeah, it's interesting stuff.
I just want to clarify that. So it's measuring the energy on a photon by photon basis of the X-rays?
Are we talking about the microcalorimeter? Or?
Yeah, the new type.
It's, sorry, repeat the question.
It's for each photon, each X-ray photon that hits it, it's measuring the energy of that particular photon.
Yes, sorry, that's another thing I didn't mention about detecting X-rays is they're so actually infrequent that you almost get them one at a time. And so that's why you're able to detect X-ray astronomy. You actually get an events list where each photon has a time and an energy, and it's relative position we think it came from. Yeah.
We have a question online. Ashok is asking, how is AI being used to analyze the volume of X-ray data?
So yeah, in terms of AI in astronomy, I think people definitely are using it with in other places like detecting like galaxy morphologies and things like that. I haven't heard it being applied to spectroscopy as much because there's so much physics that, like I said, we're still checking because there's so much we don't know. I think it'd be hard to use AI because there's not really much to train it with because we're not really sure yet. Yeah.
So in the active galactic nuclei where you're measuring the spectroscopy of the X-rays and you're seeing signals from mostly hydrogen, or are there higher elements involved in generating the signal that you're picking?
Yeah, so that's a really good question. So like I was mentioning, we're detecting are you familiar with the word like ionization? Is that comfortable? Okay. So we're actually I'm actually, if I was talking to physicists, I would call these highly ionized winds. And so when you ionize hydrogen, it's it's gone immediately because it only has one electron. So you actually can't view an ionized hydrogen in an absorption spectrum. And then because I'm looking at things that are so highly ionized, I'm also not able to see any helium. And the majority of the things we're seeing are things like carbon, nitrogen, and iron. We actually call it helium and hydrogen-like iron, because iron it's so high energy in this region that iron has lost it's lost like almost all of its electrons, and it's only down to like 1 or 2, and we're being able to see the absorption lines from the last 1 or 2 electrons left.
So that leads me to the second part of the question.
Yeah.
So that, do you have reason to believe that the AGN process of the physics going on there can actually lead to nucleosynthesis, or are these higher elements coming from stars that went through their life cycle in the galaxy, and then in the accretion disk, they're getting victimized by these processes? Do you know the answer to that?
Yeah, so I've definitely heard, people sometimes talk about nucleosynthesis in the context of accretion disks. And it's definitely possible that there's some nucleosynthesis going on in accretion disks, but from what I'm aware of, it's not going to be any sort of dominant process. And actually determining, like you were saying, the relative abundances of elements, that's actually still somewhat of an open question with these regions. Like for right now in my research, I'm mostly assuming if you guys are familiar with the solar abundance, which was like abundances of things like our sun, except because we get a lot of data from things like iron, we can a little bit easier check for, is there an orbital abundance of iron? But yeah, if it's not a non-solar abundance, that is definitely something I might even try to discuss in like a future paper of like, if our assumptions are wrong, what could that mean? But yeah.
But whatever gets made there, never gets out.
Well, in accretion disk, it can get out, no
Oh.
problem. Yes, in the back.
So what causes like a relativistic jet to exist?
That's a really good question that a lot of physicists near and dear to me are trying to figure out. I can give you some of the ideas. So jets are not something I personally study, but they are really cool because they make way better pictures, honestly. Where did my diagram go? Where I had the wings. Sorry to give you whiplash. But was it? Oh no, I passed it tonight. I'm sorry. Oh, I'm gonna get us all busy. Okay, so it was after, no. Okay, I'm lost. Okay, but the jets, we generally think of like, you can see sort of like, it's light in this image, but you're talking about the jets that come out of like the top of the black hole, right? That's what you're thinking about. So I don't study those, but there are a lot of ideas that, for example, there's a lot of things we don't understand super well right now. So it's kind of a running astronomy joke, I don't know if you guys are familiar with, but if you're ever in a talk and you want to try to sound smart and you don't know what's going on, you can always, at the end of the talk, just ask, well, what about magnetic fields? Because half the time, or more than half the time, we're not really sure what the magnetic fields are doing. These things are like galaxies away. But in terms of jets, it is strongly believed that magnetic fields might actually be really important to forming jets and just like collimating gas in this really constricted way, because they're so focused and coming out of that way. But again, where the jets would start is really, really close to the black hole. So it's hard to be sure yet, but there are definitely people trying to simulate things like that and narrow it down. So I'm sorry I don't have a better answer for you yet, but hopefully we will soon.
One last quick one.
Yeah, sure.
So years ago here at Princeton, we heard a lot of talks about quasars. There was all this interest about quasars and trying to figure out what they were. They're the most distant, the most brilliant. Are quasars active galactic?
Yes, so I apologize for not spelling that out in the talk. But I remember early on when I first started studying AGN, I learned from my courses that all quasars are AGN. And so that I at one time accidentally interchangeably used quasars and AGN, and my advisor had to be like, had to explain to me that all quasars are AGN, but not all AGN are quasars. And so I couldn't just switch up what I was using, because I studied something very, very close you can resolve the galaxy. So that essentially means it's not a quasar. Quasars were discovered by being, like you probably know, confusing because they look like point sources on the sky, how stars usually look. And so we originally thought they were just really, really weird stars where they got their name of quasi-stellar objects. But then once we found out what AGN were, and we realized that AGN actually explained the strange behavior of these quasi-stellar objects, we realized, okay, those things are actually not stars at all. They're actually the centers of really, really distant galaxies, like I said, that can outshine their entire galaxy. So quasars are just really far away AGN, essentially.
Thank you, that clears that up.
Yeah.
Wonders for years about it.
Yes, yes.
So we had a couple of comments online. Ted said, excellent talk, exclamation point, about a half a dozen. We had an Eileen that said, really interesting. I had no ideas that black holes generated winds.
Mhm.
And then I think someone who knows you says, so interesting and well said, from Christina Hoffman.
Wonder who that is.
Okay. Maybe, Victor, would you say we should probably wrap it and well, thank you.
Yeah, well, actually, before we break. Doing this for Ira, who feels that I should make a little ceremony of this, just handing you out. There you go.
I'm honored.
Thank you very much for being with us.
Thank you guys. This was so much fun.